Number 3 has some key wordings here. It says, if g of t equals this, find the value or values where g of t, and then the last phrasing is key, has a horizontal tangent line. Santi, I think, thinking back to what the web assign was, I think I have the answer to where the multiple x's come from, because I think it asked 2 different questions. It didn't just ask the one. I think it asked for vertical and horizontal, so it's 2 different things. We could explore that a little bit here if you want. Okay, so horizontal tangent line. Of course, we all know what a horizontal line looks like. It's flat, right? It's like the horizon. So horizontal tangent line, let's think about just a horizontal line. What kind of a slope does a horizontal line have? And so a horizontal tangent line would similarly have a slope of 0. Okay, so when you see tangent line and you think about slope of tangent line, you need to be thinking about one thing only, and that would be derivative. Slope of tangent line, whether it's horizontal or not, slope of the tangent line is this dy dx, or g prime of t here. So here we go. So I would say g prime of t equals, well, what rule am I going to have to use? Got to use a quotient rule. You don't have to use a quotient rule. You could actually use a chain rule here. We can explore that a little bit if you want, but let's go ahead and use a quotient rule. That's fine. So that would be low. And what on earth is d high?
0.
So that whole first term is just going to be 0. Low d high. Minus high. What's d low? 2t plus 3 all over the square of what's below. So that would be t squared plus 3t minus 1 quantity squared. And you could clean this up a little bit. You could say g prime of t equals, I guess you could distribute that minus 1 and get negative 2t minus 3 over this whole somewhat scary looking denominator. Okay, so there's our derivative. The reason why we found a derivative is we're trying to find out where this graph, g of t, has a horizontal tangent line and the slope of the tangent line. That is the derivative, right? So g prime of t. But we want to find where g prime of t then, based on your earlier reasoning, equals 0, right? We're looking for a horizontal tangent line. I do want to mention this. I mentioned this a little bit before. Something like this, putting equals 0, is incredibly important for what moves forward, because we're going to solve this equation here in a second. And without that equals 0, there really isn't an equation to solve. So I'd encourage you in the strongest possible terms, if you want to earn points and be recognized for your good work on grades, you want to put equations like that down. Go ahead. You might be thinking equals 0. Make sure that that thought of equals 0 works its way into your page, and it actually says equals 0. And this is what we were talking about a few minutes ago. This looks like a pretty scary equation, right, to solve. You got this fraction equals 0. I like thinking about it like this. If you do have a fraction where you've got a numerator up here and you've got a denominator down there, what is the only part of a fraction that could make the whole fraction have a value of 0? Only the numerator. The denominator cannot make a fraction equal 0. So what I would do is I would take the numerator and set it equal to 0. Negative 2t minus 3 equals 0. This would lead me to solving fairly easily and getting t equals negative 3 halves. Negative 1.5, I guess. That makes sense? Well, this is not part of this question, but I thought maybe we could talk about this as well. Let me actually get rid of this. I'll just write this over here. What if, and Santi, this will hopefully help you. What if it also asked for a vertical tangent line too? So what if it said and vertical tangent line? You set the denominator equal to 0. Remember, so here's the reasoning with that. You guys are exactly right. A vertical line has what kind of slope? Undefined. How do you make a fraction undefined? Make the denominator 0. That's exactly right. So I don't know how this is going to work out. It might not work out very well, numerically speaking, but you would set the denominator equal to 0. It'd be t squared plus 3t minus 1 squared equals 0. This would give you a vertical tangent line location, or locations perhaps. So you could square root both sides. So you get t squared plus 3t minus 1 equals 0. And I didn't intend this question to go here, so I don't know how this numerically works out. It clearly is not going to be factorable. Maybe you use the quadratic formula or something. So it'd be negative 3, t equals negative 3 plus or minus the square root of 9. I guess it would be plus 4 all over 2. So it would be real. It'd be negative 3 plus or minus the square root of root 13 over 2. Those would be your locations for t, for the vertical tangent lines. Less pleasant than negative 3 halves perhaps, but that's where you'd find them.
If we were answering a question about that, would you care if it was like in decimal form or in that form? Or
All depends on if the calculator's active or not. If the calculator's active, go for it. As a matter of fact, if the calculator's active, I would expect you just to use maybe the zero finder on your calculator and find the zeros and definitely decimals there. If the calculator's not active, I would expect you just to leave it something like that, and I'd be fine with that, 100%.
So for the horizontal tangent line, there's only one value.
True. True, yeah.
So all you have to do is t equals negative 2 halves.
Yep. So on your web assignment wanted an input and an output. And so one of the questions was, okay, so I get this t equals negative 3 halves. If I'm supposed to find the output to go with that, like an x and a y, or in this case a t comma g of t, you just take that negative 3 halves and plug it back into the input for g of t. And that would give you the output to go with that input.
Okay.
You would not plug it back into g prime, because if I took this and plugged it back into g prime, what should I get? I better get 0, right? Because that's where it came from. So I'm not going to be plugging that back into any g prime stuff. I'd plug it back into g of t's input. Okay, how are we doing? Any questions? Yes? No? Okay, cool. All right, well, let's jump ahead a little bit. I want to do one or two of these implicit differentiations. You going to join us? You going to do?
Oh, yeah.
So the only way you can really get good at math is if you do. If all you do is spectate, it's not as good. Please don't make me tell that to you twice. You should just do that automatically. Okay, I would like to do this one, number 4. I think this is a really good one for us to kind of explore a little bit and think about all the different ways this could go. So number 4, we are jumping around a little bit, but check this one out. This says, find the equation, I underlined it for you, of the normal line. I want to explain a little bit about what that is. If you've been in physics, you might know what this is. The word normal in math or physics doesn't mean like regular. What does it mean? Perpendicular, yeah. Perpendicular. So finish what you said there. Specifically to the tangent line, yeah. So I'll put that right here. I'll put perpendicular to tangent line. That's what normal means. So if you've ever been in a physics class, you guys ever like worked with the normal force? So that's the same thing, right? So it's perpendicular to the surface that whatever the object is on, and maybe you remember that friction depends on what the normal force is, like the force perpendicular to the inclined plane or the horizontal whatever. I mean, so same sense of the word here. So let's think this through. If we go off what Eden said, that the normal line is perpendicular to the tangent line, if I could find the tangent line slope, couldn't I then just like manipulate that a little bit and then I'd have this normal line slope? Think about that reasoning again. If I know that the normal line is perpendicular to the tangent line, doesn't that mean their slopes have a relationship? Yeah, the opposite reciprocal. That's exactly right. So if I could just find the tangent line slope, couldn't I just do that whole opposite reciprocal thing? And then I'd have the normal line slope, right? So I want to approach this from 2 different ways, and that would be the first way. So if I am looking for, I'll just put it like this, find the tangent line slope. Symbolically, how would we represent the tangent line's slope? What symbols? dy dx specifically. So I'll just put something like find dy dx. That would be our kind of our first mission here. If I can find dy dx, then I can use that whole opposite reciprocal thing, and then it'll be over with pretty quick. So I've got this x squared plus y squared equals 25. And what is that the graph of? It is. It's a circle. Of course, this is defined implicitly, and so I think probably your best move, I really do, I think your best move is to use implicit differentiation. I'm not just pulling your leg. I think that is easier than trying to solve for y and go through that whole routine. It's going to cause more trouble.
Would you get the same answer?
As long as you handle the plus minus correctly, right? Because in the process of solving for y, you'd get plus or minus the square root of 25 minus x squared. Then you got to think about which quadrant am I in, so should I use the plus or the minus? You got to not mess up the plus or minus, and then eventually you would get there. But it would still involve a chain rule. I think it's easier just to do implicit. I really honestly do. I am not being the teacher that's like, I'm telling you it's easier, but in my heart I believe it's not. I really believe this is easier. If you catch on, I think it'll really work well for you. So if I'm looking for dy dx, what am I going to do? ddx, that's right. If I was looking for like dy dt, I would do ddt, right? So whatever that denominator symbolically is, that tells me what I need to do. So I'm going to do ddx of this whole thing. So let's go through and see how much we remember from last time. We did one really similar to this. What would you guys say ddx of x squared is? 2x. That's right. How about ddx of y squared?
2y times dy dx.
Yay, there we go. And that's equal to 0, because ddx of a constant, 0. All right, so maybe we go about it like this, and we say, all right, we're going to solve for dy dx. So solving for dy dx, I'd have to subtract the 2x over, divide by 2y. I end up with negative 2x over 2y, which is equal to negative x over y. And that right there, my friends, would be the slope of my tangent line. What do you think? I mean, going from here to here, I did use some pretty basic algebra solving. It's worth mentioning if there's any struggle. Basic does not mean easy. It might mean difficult, yeah.
So when you get dy dx, it's like you're using a chain rule? Or?
It's exactly what you're doing.
Okay,
Yeah.
just, so it's like y.
Y is like your inside, and so
And then-
ddx of y is dy dx.
Okay.
Exactly. It's a chain rule where that comes from. Yeah.
We use y primes to make it.
So I think specifically in a case like this, it probably doesn't matter too much. I noticed you were doing that there. It's going to matter huge in 2-6. Use Leibniz's notation. I would strongly encourage you,
Okay.
because you're going to look at y prime and you're like, well, is y prime dy dx or is it dy dt? And you're going to want to know the difference between the two, and sometimes you might have both of them in there. I think Leibniz's is better in this situation. In this case, I don't think it makes too much of a difference. Okay, so would it be fair to say that this is the slope of the tangent line for the circle at any x or y value, right? At any point. I don't really care about any point. What do I want to know about? Yeah, my point of tangency, which is right there. So I could then say, have you guys, I think you've seen this. If not, this will be good. Have you seen this sort of notation where it says dy dx evaluated at 4, -3? Have you ever seen that vertical line? Have I shown that to you yet? I can't remember if I have or haven't. So that vertical line just means evaluated at or evaluated from this to that, depending on the situation.
Would it be incorrect if you gave the function a name and then after you had solved for dy dx, you called it like f prime?
It gets really complicated, though, because how would you give it a name? Like, where would the name go? Would you just, like, tag this on the end and put equals g of x?
Well, because didn't you say that dy dx is like, it is the derivative of the function, so if you...
It is. So there is an answer to my question. I'm not saying that you can't do it that way. What I am saying is if you were going to name it, you'd probably want to name y. It gets really complicated.
Yeah, like if you saw like...
Like having seen what I've seen, that's going to create more problems than it's worth.
Okay.
I think. Now, if you replaced y with like g of x, you might be able to navigate your way through that. But like I said, it creates a lot of like symbolic issues. You're like, well, wait a minute, is that really the output? And could I solve for that? And you end up juggling a lot of different mathematical symbolic, it's tough.
Okay.
It really is. This notation is very standard, right? So like worldwide, like notation of like vertical line means evaluated at. It's pretty typical. So that if you do actually evaluate this, what do you get, 4/3? Okay. So that right there is the slope of the tangent line. And because I'm supposed to write the equation of the normal line, this is where I need to do that little trick and say, oh, that's the slope of the tangent line. I need to flip it and change the sign. So I'm going to put up here something like the slope of the normal line. Does that symbol make sense? Perpendicular M. I'll circle it a little bit better. Perpendicular M. Slope of normal line. Yes? This is one way you could do it. Perpendicular slope is equal to -3/4. And once you've got that, and you've got your point of tangency, hopefully this would be a pretty quick finish, right? So you could write y minus -3 equals -3/4 times x minus 4. That'd be the equation of your normal line. Can I show you some other symbolic stuff here? If you guys didn't like this whole perpendicular M thing, maybe you didn't like that, I want to see what you think of this.
Do you have to define that? Like if I wrote out after I found the slope of the tangent line and then said like this is the equation of the tangent line and then just went straight from there to the equation of the normal line because you could just flip it, would that be wrong?
No. That's not wrong at
So
all.
you don't have to define, like, this is the slope.
I think it's best to not have floaties, just like numbers that have no like meaning attached to them. I don't think that that's the greatest idea. What you described is okay though, I think. What do you guys think of that symbol? Negative dx over dy. So think about it. Didn't I find that dy dx was 4/3? So if dy dx is 4/3, wouldn't dx dy just be the reciprocal of that? And negative means opposite of that. So you could write it like that. In fact, negative dx dy would be considered the slope of the normal line. So what we could have done, I'm not going to do this, what we could have done is we really could have said, hey, I'm looking for dx dy, because we're looking for slope of normal line. And instead of doing ddx, I could have done ddy. Now, I don't think that would really save much time, because if you find dy dx, all you got to do is flip it and change the sign. I don't think that saves a whole lot of time necessarily, but it could have been a different approach. It would have worked just fine.
Would you have to do negative?
You just change the sign in the end. So you still got to change. That's why I say I don't really think it would save you any time. It would just be a different thought process leading to the right answer.
Gotcha.
Yeah. Okay, questions, thoughts? We're going to do one more of these implicit differentiations, I think. At least one more. We'll see. We good? Okay. Let's see here. So I would like to do the one with the ellipse. So if you guys turn back to number 3. So we've done 2, we've done 4. Okay, this is perfect. Perfect. Okay, so here's number 3. Yeah, I'm assuming, do you guys do conic sections? Like hyperbolas and ellipses and circles? Did you do that like pre-calc probably? Yeah, okay. So do you guys recognize that as an equation of an ellipse?
No.
You spent 1 week on it?
Yeah.
Yeah. So you don't have to be like super well versed in like, hey, this is an ellipse, this is hyperbola. I mean, it calls it an ellipse. All the stuff we're going to do, it really doesn't depend on your expertise with graphing an ellipse. But does anybody know where the center of this ellipse would be?
2, 8.
Not 2, 8. I think I heard. No? I catch little bits and pieces. Anybody confident? The center's at the origin. Agreed. So the reason why I know that is because it's not x plus anything squared or y minus anything squared.
Oh.
Right? So it's just like essentially x plus 0 squared. Again, all these details, I'm just kind of curious. You don't have to be an expert at this to be able to execute the calculus. So it is centered at 0, 0. And then does anybody know what the 2 and the 8 have to do with?
How, like, the horizontal distance?
Yeah. Basically, is it a tall, skinny ellipse or is it kind of a short, fat ellipse?
It's tall.
Right? So what would you guys say? Is it tall and skinny or is it short and fat?
It's tall.
It's actually tall and skinny because the number under y squared is bigger than the number under x squared.
Can't these be written as, like, or what's the one that could have been written, like, you could have had the y first, and then if it's, like, negative, it means...
Oh, that's hyperbola.
Oh.
The sign of the x squared and y squared makes a difference. But since these are both positive, it's an ellipse. So what this one looks like, just real quick, just a real rough sketch. This looks like a tall, skinny ellipse. Maybe, whoops. Something like that. The left side's pretty good. The right side is a little regrettable. I'm going with that one. It is hard to draw these things. Okay, so there is roughly the ellipse graph. And so then I've got this equation, x squared over 2 plus y squared over 8 equals 1. And it says, similar to the question we just talked about, find the equation of the tangent line. So if we are supposed to find the equation of the tangent line, what are the two things we've got to have? Slope of the tangent line and point of tangency. I've kind of sort of given you one of the two. Which of the two did I just sort of halfway give you? The point. Yeah, so it says when x equals 1. So my point of tangency is going to be 1 comma something. How would I find the y? Yeah, plug the x into the function. So we're going to have to make a decision here in a second, and I'm going to let you guys decide what you want to do. So I'm going to plug that 1 in. So it's going to be 1 squared, which is 1. 1 over 2 plus y squared over 8 is equal to 1. How do you solve an equation like that? What might be your first step? I know it's tempting to subtract the 1/2. I suppose you could do that. Let's do that. It's okay. Why don't we just multiply the whole thing by 8? You want to just get rid of the fractions? I want to get rid of the fractions. Is that okay?
Yeah, me too.
Okay, so we multiply the whole thing by 8. You get 4 plus y squared equals 8, right? Because the 8 and the 1/2 would cancel to be a 4. The 8's cancel. 1 times 8 is 8. And then you get y squared is equal to 4. So y equals
2
plus or minus
plus or minus.
2. So this is where I didn't make it clear because I wanted us to decide. Do you guys want to go with plus 2 for our point of tangency or minus 2? Plus 2, fair enough. So in a quiz or a test, I'm not going to give you that decision. I'll kind of tell you.
Don't you need, because if it was -2, wouldn't that be in the other?
Yeah. So 1, 2 is right here. 1, -2 is down there. So you guys decided to use the quadrant number 1. That's fine. We could have done both of them. Let's just do quadrant 1.
But doesn't you have to do the first quadrant because it's not what it's saying?
Does it say first quadrant?
Yeah.
Oh my gosh.
Oh, 'cause
Is
I
this-
thought you were like, you can do either. I was like, wait.
You know, this is proof that I don't rehearse these questions ahead of time. I just read right over that and just didn't even... Let me just underline that for those that similarly did not see it. So we'll go with first quadrant.
Yeah.
If it said fourth quadrant, we'd have to go with -2. Fair enough. Okay, so I'm going to erase that arithmetic there, that algebra. Is that all right? Just to give myself a little bit more room. Okay, so I found my point of tangency is 1, 2. And now I've got to find, as you guys mentioned earlier, the slope of the tangent line. And this is where there's going to be a little bit of calculus involved. I like the idea that was put out there a few minutes ago about I don't like the 2 and the 8 denominators. So before I do any calculus, I think I'll do the exact same thing and just multiply the whole thing through by 8. It'll make it a little bit easier. So if I do that, are you guys okay with me writing 4x squared plus y squared is equal to 8? Just clear out the fractions by multiplying every term by 8. Is that okay? Is that logical? I want to make sure that that makes sense. Okay. All right, so then we're trying to find the slope of the tangent line. Can you guys tell me what the symbol is for slope of tangent line? dy dx. The problem with that, of course, is we don't have an equation that is currently solved for y, and so we have to use implicit differentiation. You don't really have to here, but I think have to from the perspective of it'll be the most efficient method. Okay.
What is the 4 from in the equation?
So I multiplied, I'll put parentheses up here. I multiplied this whole equation by 8. So when I multiply 8 times 1, of course I get 8. When I multiply 8 times this term, the 8's cancel to be a 1. When I multiply times this term, the 8 and the 2 would cancel to be a 4 in the numerator. It's like 8 over 2, essentially, 8x squared over 2. Is that good? Okay. So because it's more convenient to use implicit differentiation here, that's what I'm going to use. So you tell me, if I'm looking for dy dx, what do I have to do? I got to do ddx. So I'm going to do ddx to this whole thing. And again, I'm going to see if you guys can handle the details. What is ddx of 4x squared? That's right. How about ddx of y squared? 2y times dy dx. And ddx of 8 is 0. Okay, so to solve this, I need to add or subtract the 8x over, divide by 2y. Dy dx ends up equaling, negative 4x over y? Does that look right? Okay, so then I want to know what the slope is at my point of tangency. So that would be dy dx evaluated at the point 1, 2. And let's see here, that would be -2. Look good? So then my full equation of the tangent line, I would use my point of tangency and my slope of the tangent line. I would get y minus 2 equals -2, parentheses, x minus 1.
Wouldn't it, for all of these, wouldn't it be? Never mind.
Sure?
Because like if you were gonna write it in like y was mx plus b form, it would be 0 for like b would be 0.
I don't think so.
No.
It'd be 4. Because you'd get -2x plus 2, and then you'd add 2 over. So you'd get -2x plus 4.
Isn't point 1, 2?
1, 2. Yeah. You can take that and solve it. I think you get y equals -2x plus 4. Maddie, go ahead.
Where does the -2 come from when you do like the dy dx?
So this one right here.
Yeah.
So this down here that I'm putting in the red box, that is the slope of the tangent line for any x or y. So like a general derivative. So if I pick any point along this ellipse, then I could use that point and the negative 4x over y to find the slope at that particular point. I want to know, however, the slope of the tangent line at my point of tangency, so at the point 1, 2. So what I'm doing is I am taking 1, 2, and I'm plugging in a 1 for x and a 2 for y, and doing a little arithmetic and coming up with negative 2. Great question. Anybody else?
What is it saying then when it says use this name?
Yeah, we'll do that next. Yeah, we'll get there. So we've done one sort of like that in the past, but we'll revisit here in a second. Are we okay with finding the equation of the tangent line? Okay. All right. So then, what do I do with it? This is where it asks us to take one more step. It says, now use that tangent line to estimate y of 1.1. So I am going to, I'll sketch the tangent line in. Actually, I'll do this. So Anna, you were asking about kind of the form of it. Does that form make sense now?
Yeah.
Okay, so there's my y equals negative 2x plus 4, my tangent line right there. So we talked about this in the past, about how you could use that tangent line to estimate the y value of the curve. So let's see here. That was, point of tangency was 1. So 1.1 is just going to be slightly over here. I'll make it a red dot. So this would be like 1.1 right about there. You guys see that little red dot? So then wouldn't you guys agree then that the y value of the line is a little bit above that? So when x equals 1.1, the line is different from the curve. So I totally get that they're different, but I am asking you to estimate. So I don't expect this to be perfect. So what you actually do with this is, to generate your estimate, you would write y minus 2 equals negative 2 times 1.1 minus 1. We're just going to plug the 1.1 in for x. I'll come over here. 1.1 minus 1 is 0.1. And what's negative 2 times 0.1? Yeah, negative 0.2. And then you add the 2 over and you get y equals positive 1.8. And that means that y of 1.1 on the curve is approximately equal to 1.8. So I hope you remember I was doing this before. So here's the principle. At the point of tangency, aren't the 2 points the same? The point of the curve and the point of the line are the same. I have moved off the point of tangency a little bit, right? So isn't it totally fair to say that whatever the y value of the line is, the y value of the curve will be something different? All we're doing here is we are estimating. We're building this towards being able to estimate stuff that we don't know as much about, like this. We do know a lot about this, and we could easily find it using a calculator, but we don't know about it right now, so we're working on estimating.
Would it be
So I want to focus on the, is it too high or too low? So is that estimate of 1.8, is it higher than the actual value of the curve, or is it lower?
Because wouldn't it be stupid?
Well, so we're not talking about slope of anything, we're just literally talking about the y value.
Oh.
So like right here, I would say that when x is 1.1, the line is a little higher than the curve. Now if I drew this in different places, like if I had a tangent line down here, like if we had done fourth quadrant, wouldn't you say down there, wouldn't you say the line is a little bit lower than the curve? So it all depends on where it's drawn and how it relates with the curve as whether it's higher or lower.
So it's about whether or not the y value is higher or lower than
Instead of saying y value, because I know there's 2 y values here, there's one for the line and one for the curve, I'm going to say the line is higher than the curve. So because the line is higher than the curve, my estimate is too high.
I'm confused that like the line is higher.
So like right in here, right here around my point of tangency, sorry, it's a little too dark, wouldn't you say that the lines, the y values for the line, are always higher than the y values for the curve?
Yeah.
So that's why. So we use the line to estimate the curve. And since the line, at least in that area, since the line's y values are always higher than the curve's y values, I'd say my estimate of 1.8 is a little too high.
So the tangent line of like the point -1, -2 would be always lower.
Down here? Yep, the line would be too low down there. Yep. So we'll dig a little bit deeper into that into the future, but again, I just wanted to kind of get you started with that. Is it too high or too low? Get you starting to think about how we could sort of put some bounds on our estimate. Okay, how we doing? You working? Okay. So let's push ahead into 2.6. We may or may not have to do the last example in the implicit one, the number, whatever it was, 6 or 5. I don't know if we have to really do that one. We'll just kind of see how it goes. Okay. So I'm excited to get here because this is going to be the first moment when you look at this and you think to yourself, oh my goodness, all this stuff we've been working on is highly applicable. In fact, to do stuff in the real world, most of the time, you have to use calculus. The real world operates on that basis for the most part, especially if you're dealing with continuous data versus discrete data. And this is our first example of where we could do something that is highly real world.
What would be an example of like continuous data?
Well, something that could be modeled by a continuous function, like the value of a stock, right? It can have like fractions of a penny. So discrete data would be like the number of items sold from a store. You can't sell like 7.8 bottles a pop from a store.
Oh, so it has to be whole numbers, or is it?
So discrete is whole numbers. Continuous would be like any value could be taken on. So we mainly deal like for these applications, we mainly deal with just only continuous
You
functions.
could have continuous data on not a continuous function.
Yeah. Right, depending on what the discontinuity is. Let's not get too stressed about that right now. Okay, so we're going to spend about 2.5 to 3.5 days on this. This is called related rates. I just want, and listen, the reason isn't because it's like so insanely difficult. The reason is there are lots of different scenarios to be played out here, and I want to show you a lot of scenarios. That makes sense? A lot of different examples. And I've got some like this long, explanation here. Some steps and stuff, and we'll go through those things, but it's going to be easier for me to kind of show you, and we'll kind of reflect back on the steps and be like, oh, okay, now that makes sense, that kind of thing. So I wanted to start off by trying to interpret the meaning of symbols. These could mean all kinds of things. DLDT, I'll just give you some examples here. I would say DLDT could be the rate of change of lemons with respect to time. These are just all for instances. It doesn't have to be lemons, but I see DLDT and I think to myself, L could stand for the number of lemons. So this could be like a farmer with a lemon grove, and the weather is doing weird things, and the production of lemons is either going up or down. We're trying to figure out the rate of change of these lemons being produced because it would matter to the farmer, right? If he's getting a rapid increase or a rapid decrease in the number of lemons he's getting, could be good or bad. Could be something somebody might care about. It could also stand for the rate of change of lions in the zoo or in a game preserve or wherever with respect to time.
Do you usually have like the same letters, thing you have like the rate of change of?
I think it makes a lot of sense. That's why we're doing
Does it make
this.
a lot of sense to do that anymore?
Because if we're talking about the rate of change of people named Nick, and I represent it with like DX, DT, we'll be like, well, what did the X stand for again? People named Nick? Like, why wouldn't we just use the letter N
Yeah.
for Nick or number of people named Nick or something like that? P, sure. So it could be the rate of change of puppies. I like it. Well, maybe they're being born.
Maybe maybe one gets bought every hour. And then,
Yeah, pet
so
store
like
has a
clothes.
whole pile of puppies and they're trying to sell them. They have a sale. And what's the rate of change of puppies? Maybe they're being born. Maybe you're looking at it from a macro scale and you're like, in the state of Colorado, golly, the rate of change of puppies has really been increasing lately. Why is that? Maybe they should be getting spayed and neutered or whatever. Maybe we need to do an initiative so there's fewer puppies out on the street. I don't know.
Would like a company say like the rate of change of puppies based on like how fast they're being born?
Right.
And, like, could they put that on a graph and like compare that to the rate of change of like how fast they're being bought?
Yes. Oh my gosh, what a great calculus question that would be. Basically, you've got a rate coming in of them being born. You've got a rate of them leaving, so you could look at the net rate of the puppies in the store. Would be a great calculus question.
How would you compare the graph?
So the net rate would be rate of puppies coming in minus rate of puppies leaving. We'll do questions like that for sure. It would be a great calculus question. In fact, I might even have one about bunnies. I can't remember if it's in this class or in BC. Bunnies being born and bunnies dying or something like that. Anyway, hey, what would you guys suggest for DNDT? I want to hear like an exact thought as far as DNDT. What do you think it could mean? And we want to be really careful. I want to hear exactly what you think I should write. Oh, I like how you started that. So, of notebooks. So, hey guys, hey listen really carefully. This is going to seem so minor, but I'm hoping that you have gotten to a point in here where you realize that especially in this class, I hope it would be true in pre-calc and other classes too, but especially in this class, details really matter, do they not? So if you looked at DNDT and you just wrote notebooks, like that's all you wrote, I would say you have a massive issue with interpreting what that means. I agree that the N maybe would stand for notebooks, but DNDT certainly would not stand for notebooks.
Could you just write like delta notebooks with respect to time?
I don't know. I'm never going to ask you to like write out a sentence like this necessarily. I'm more talking about the way you think about it. If the way you think about it, if you look at that and you're like, oh, that's notebooks, I think you're going to stumble. But if you look at it and you say, the rate of change of notebooks with respect to time, if that's the way you self-talk this out, like that little voice in your head that kind of directs you on what you're supposed to do, then I think you're on the right track. The rate of change of notebooks with respect to time would be a really great interpretation. But if you just say, yeah, it's notebooks over time, really, you can do better than that. You can do a lot better than that. It's got to be a rate of change because we are talking about various derivatives here. It's a rate of change with respect to time of whatever the N, P, or L, or C, or B, or whatever it is happens to stand for.
In these situations, would it always be like over dt or could it be like over delta d or something?
No, I don't think so. We're going to use the calculus symbol, like the dt, because we are talking about at a point in time. What's happening when t equals 5 seconds, rather than what's the average rate over the interval from like 2 to 7.
Yeah, but like if it was a situation like with like the puppies, if it was like these puppies on a like going a distance.
Yep.
And then like how many puppies were at this distance? Could you do that, or is it just like with time?
Usually it's going to be with time. It could be. There are a few oddball examples I can think of where they're really messing with you on units. I'm thinking of AP tests, just to see if you understand what the symbols would mean. So yeah, like it could be like DNDL. It would be the rate of change of notebooks with respect to people named Lori. I don't know why anyone would be interested in anything like that, but it could be that, right? But I'd say it's extremely common to be with respect to time, simply because time is independent of everything else. Time, you guys know this, right? Time does not depend on anything. It's always just going. And so it's always going to be a very dependable, independent variable, right? It's always just doing the same thing the whole time. Versus the number of people named Lori could be going up and down, and maybe we don't really care about that. But time, consistent. Okay. Unless you're traveling near the speed of light, then not consistent. Anyway, so then the last one, what do you guys think? Rate of change of? Smiles, happy people.
With respect to teaching math.
Okay. So it's got to be the rate of change. That's a non-negotiable. You could say of happy people with respect to tacos. Ooh, that's a good one. As the number of tacos increases, the number of happy people tends to go up as well. Whatever. Okay, so like I mentioned, there's this whole long thing here about related rates and how to deal with this. I'll just blast through this. It's so much easier just to do these and see the steps within the doing of these than it is to try to just read the steps. It's kind of not very effective. So let's just briefly read through these. I'm just going to tell you, what we're going to do is we're going to start off by trying to figure out what the general point of the question is, just the story of the question. And then, for some of you, this is going to be highly comfortable, and for some of you, this is going to be very uncomfortable. We are going to mark the question up. In other words, we're going to go into that question, we're going to underline stuff, we're going to circle stuff, we're going to put a box around things, and we're going to interpret that stuff. Have you ever looked at a word problem, kind of a bigger word problem, like some of the ones maybe you've seen ahead, and you kind of freeze up a little bit? Yeah? Listen, I know she's got to go. Just go quietly. It's fine. Listen carefully. Come on. She's just going to leave the room. I want to give you a way in which you can look at one of these scary-looking paragraphs and break it down into little chunks that you can use, that you need, and bottom line, to make it more understandable and easier. I think this is one place where math teachers kind of fall a little bit short. I don't know if you've ever heard this, but sometimes a math teacher will be like, hey, here's a paragraph, read it and figure it out. Like essentially that's what they're saying. Just read it and figure it out. Not so easy, is it? Not so easy. And so I'm going to try to give you some tools that will help you say, okay, beyond just the whole reading and figuring it out, what are some key pieces I can draw out of this thing that I can use? Make sense? So let me give you this system here. We'll look for all these key pieces. You'll see all these kind of come through when we work on these. I'm going to skip around a little bit. We are definitely not going to do number 1 first. We're going to do number 2. This is a good one. Okay, so the first step that I would encourage you to do is don't worry about the fact that this is a math question. It's obviously just 2 sentences, but it is a word problem, therefore has the potential to be challenging, right? So I just encourage you to read it through, try to figure out what's going on in general. Don't worry about math. Don't worry about numbers specifically too much right now. Just read it through and figure out what's going on, and we'll discuss it here in a second. Class is over at 25, right?
Yeah. Chopper just got out.
That's what it is. Why is it so loud out there? Okay. So what do you guys think? Can anybody, in a very brief, in your own words, way, describe what's going on?
There's a cube, 2 by 2, expanding by 6 meters per minute.
That's even more, that's right, but that's even more specific. I'm just thinking, and you said it, there's a cube and it's expanding. Isn't that the general plot here? Some of the plots will be a little more complicated than that, but there's a cube and it's expanding. That's it. So this might be a case where a picture is useful or not. Sometimes we'll draw pictures of these. So I'll just sketch one out really quick. This is the classic 5th grade. Oops, let me retry that. This is the classic 5th grade sketch of the 3-dimensional cube. Oh, messed that part up. So here, 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 and here. Here's my cube. And it's expanding. Why is it expanding? I don't know. Maybe it's being heated up. Maybe it's made of ice and it's cooling off or something. I don't know. It's expanding. Maybe it's a part of an engine. Maybe it's an aluminum part in a cast iron engine block and it's expanding. And we have to figure out, is its rate of expansion going to be too fast or fast enough or too slow or slow enough, whatever. There's a million different ways this could go. But basically there's a cube and it's expanding. The next thing we're going to do, this is the key step I think, is I want to read through the question and ask ourselves, what is this question asking me to find? And I'm going to put a box around that. So can you guys identify it? There it is. How fast is the volume changing? And this is where our skill with interpreting variables and symbols is going to matter. How fast is the volume changing? That's a rate, right? How fast is something changing? So I want you to think for a second, what calculus symbol, kind of like the dNdt, dLdt, dPdt thing we just looked at, what calculus symbol might be a good representative of how fast is the volume changing? dV dt. We're talking about time, right? So it says per minute right there. So we're talking about with respect to time. So I'm going to say that dV dt, that is my unknown. That's what it's asking me to find. So I'm going to write that down. I put a box around how fast is the volume changing, because that's what I'm supposed to find. And I interpreted that as dV dt, rate of change of volume, right? Does that make sense? Rate of change of volume. The next thing we're going to do is we're going to look through the rest of the question and ask ourselves, are there any other rates that might be important? Because these are called related rates. So maybe there's more than one rate in play here. Do you see any other rates? Any other words that indicate that there's a rate? What do you see, Al Young?
6 centimeters per minute.
And what told you that that was a rate?
A rate of 6.
It just comes right out and says it, doesn't it? Now, this might seem painfully obvious, but until you break it down in these little pieces, it can be pretty darn difficult. So it does say at a rate of 6 centimeters per minute. And what is it? The edges. So the edges would be like these little line segments that constitute the cube's shape, like the framework of the cube, those E's. So if we call the edge of the cube E, like just the alphabetical letter E, and we look at what Ah Young pointed out, that the edges are expanding at a rate of 6 centimeters per minute, how could I write that using sort of like a dV dt-like symbol?
Over dt?
dE dt, rate of change of edge, yes. dE dt is the rate of change of the edges. And we know what this is. What is this? 6. Now it's specifically positive 6. Why would it need to be positive 6 and not negative 6?
Positive means it's expanding.
Expanding, that's right. The cube is getting bigger, not smaller. So if the cube was shrinking, then we'd have to make that a negative 6. But it's positive because the cube is expanding. The last thing here is what I like to call the freeze frame moment. The freeze frame moment is where we're going to say, and what's happening now? We're going to kind of pause it, right? So what do you think the freeze frame moment for this would be?
When each edge is choosing.
And what's the key word that told you that, Nick? When. That's it. Yeah, when. So I am going to circle this when each edge is 2 centimeters. I'm going to say that my freeze frame moment is when E equals 2. So I like to think of this like a movie. Like you're on Netflix or YouTube or whatever, and you want to watch a video of some kind. And what we've done so far here is we've kind of thought about the different elements of the movie we want. We want it to be about a cube, and we want it to have volume. We want it to have edges. You know, we got all these elements here. And so sometimes this step is really easy. Sometimes this is challenging. But I've got all these elements in regard to a cube. I've got volume of a cube. I've got edges of a cube. And what we have to do is we have to try to relate these things. This is going to finish pretty fast. If I'm going to try to relate the volume of a cube with the edge of a cube, what relationship, what equation relates those two things? Yes, the volume formula for a cube. Volume equals E cubed. So along the movie analogy, I like to think at this point, I was looking for a movie about volume. I was looking for a movie about cubes and edges, and I just found it. It's the movie called V equals E cubed. I know it sounds really exciting, worthy of watching for sure. There it is. We picked out our movie. Now here's the analogy. In order to watch the movie, don't you have to push play? Don't you have to push a little triangle? So to further the analogy a little bit further, the way that we push play, check this out. The way that we push play is we do DDT. In other words, we get time moving, right? So like you select the movie and the time is not moving. As soon as you push the little triangle button, time starts going and the movie plays. What would you guys think DDT of V would be? It's dVdt. Correct. What would you guys guess DDT of E cubed would be? 3E squared times chain rule factor? DE dt. Here's the beauty of this. Because we put so much effort into the front end of like marking the question up and identifying and pulling out all the stuff we need to know, the finish is actually really easy on this one. So I'm going to say, all right, well, I want to know dV dt. So I'm going to say dV dt at my freeze frame moment. That would be when E equals 2. Well, gosh, there's a nice input right there for E, so it'd be 3 times 2 squared. And because I put so much effort into the front end, I know exactly what dE dt is. That's 6. All I got to do now is to multiply this stuff out. 3 times 4 is 12 times 6 is 72. The final thought here would be, what kind of units would go with that 72? Yeah, because it's rate of change of volume with respect to time, so it would be centimeters cubed per minute. That's exactly right. And that would be the rate of change of volume at that particular point in time. So you guys were doing a good job. That was a lot of good back and forth, but can you see how there's a lot of different scenarios to play out here? We'll look at those over the next 3 days, okay? Hope you guys have a good rest of your day.